Welcome back to Fundamental of Mechanical Design. This beam has three things going on at once: a pin support, a distributed load, and a point load. So it's a great problem for practicing the full shear force and bending moment routine. We've got a pin at A, a roller at B, 9 meters apart, between 2 and 5 meters. There's a distributed load of 0.8 kilonewtons per meter. And right at 7 meters, there's a point load of 1.5 kilonewtons. The question asks for the shear force diagram, the bending moment diagram, and the magnitude and position of the maximum bending moment. The plan is what we had done in the first worked problem before. First, we find the support reactions using the overall equilibrium. Then we build the shear diagram, then the bending moment diagram, segment by segment from left to right. Step 1, the support reactions. Let's first redraw this diagram. First, we replace the distributed load with its resultant. The uniform distributed load covers 3 meters from 2 to 5 at 0.8 kilonewtons per meter. So its resultant is 0.8 times 3, which is 2.4 kilonewtons, acting at the centroid of that loaded length. It is at 1.5 meters from this point, and so 3.5 meters from point A. At the supports, we have RA and RB. Now, sum of moments about A counterclockwise positive equals 0. Let's build this term by term. RB acts upward at B, 9 meters from A, so it rotates the beam counterclockwise about A, positive RB times 9. The 2.4 kilonewton distributed load resultant W at 3.5 meters from A, that's clockwise at A, so minus 2.4 times 3.5. And the 1.5 kilonewton point load downward at 7 meters from A, also clockwise, minus 1.5 times 7 equals 0. Now we solve for RB. 2.4 times 3.5 is 8.4. 1.5 times 7 is 10.5. Divide by 9. RB equals 2.1 kilonewtons, positive upward, matching the direction we assume. Then we apply the equilibrium of the linear forces. Sigma Fy equals 0. Upward positive, Ra plus Rb, minus the 2.4 kilonewton resultant, minus the 1.5 kilonewton point load, equals 0. So Ra equals 2.4 plus 1.5 minus Rb. We have Rb 2.1 kilonewtons, so giving Ra equals 3.9 minus 2.1 equals 1.8 kilonewtons, positive upwards. Step 2, the shear force diagram. First segment, from A up to the start of the uniform distributed load at 2 meters. Remember the sign conventions for the internal shear V and internal moment M, V downwards and M counterclockwise. So only Ra acts on this free body, 1.8 kilonewtons plus the shear V. Sum of vertical forces equals 0. Thus we have V minus Ra equals 0. So V equals Ra, which is 1.8 kilonewtons. It comes out positive, so shear is a flat 1.8 kilonewtons across this whole segment. Now for the second segment, the cut sits inside the distributed load from 2 to just before 5 meters. So our analysis now is for the internal forces at every position X in this segment. Note that this length is not 3 meters. And now the question is how to calculate the equivalent point load, as we need to know the length of this segment here. We know that each arbitrary location here is at distance x from point A. So if our analysis is at this edge, which is x from A, then this segment length is x minus 2 meters. Thus, we can replace this distribute force with a single point load of magnitude 0.8 times x minus 2, and it's located at the midspan of this segment. Therefore, sum of vertical forces equals 0. V minus RA plus 0.8 times x minus 2 equals 0. And V equals RA minus 0.8 x minus 2. From this equation, at x equals 2 meters, this becomes 0. So V is 1.8 kilonewtons. So the graph will start at the same 1.8 kilonewtons. And at x equals 5 meters, this becomes 3. That's 1.8 minus 2.4, which is minus 0.6 kilonewtons. Let's put this value in the graph, where at 5 meters, it is negative 0.6 kilonewtons. And that the shear falls in a straight line between those two values. And here's the key move for this whole problem. Shear force crosses 0 here inside the segment of this uniform distributed load. Remember relation between shear and moment? Shear is gradient of moment. And this means we can find the maximum moment or minimum moment when its gradient is 0, or V is 0. So from this equation, when V is 0, which is 1.8 minus 0.8 times x minus 2 equals 0. And solving for x gives x equals 4.25 meters. So this is where we'll find the peak moment, and we will check that again when we plot the bending moment diagram. For the third segment, we have passed beyond the distributed load, and so we can replace this with a single equivalent load at the midspan between 2 and 5 meters. 0.8 times 3 equals 2.4 kilonewtons. Again, sum of vertical forces equals 0. We have V plus 2.4 minus 1.8 equals 0. And so V, 1.8 minus 2.4 equals minus 0.6 kilonewtons. So it is minus 0.6 constant across this segment. For the last segment, past the point load, the free body now carries the 1.5 kilonewton point load. Again, sum of vertical forces equals 0. We have V plus 2.4 from the distributed load plus 1.5 from the point load, and minus 1.8 equals 0. So V equals 1.8 minus 2.4 minus 1.5 equals minus 2.1 kilonewtons. So from 7 to 9 meters, the shear is constant at minus 2.1 kilonewtons. Remember the concept again. At the point load, there must be a jump with the amount of the point load magnitude, 2.1 minus 0.6, giving us 1.5 kilonewtons. And this can be your built-in check for your calculation. Step 3, the bending moment diagram. For every segment, we sum moments about A, and RA itself acts right at A, so it has 0 lever arm and drops straight out of every one of the equations. Let's start with the first segment from 0 to just before 2 meters. Sum of moments about A, counterclockwise positive, equals 0. The shear V acts downward at the cut, a distance x from A, that's clockwise at A, contributing minus V times x. The internal moment, M, counterclockwise positive, contributes plus M equals 0. So M equals V times x, with V equals to 1.8 kilonewtons here, M of x equals 1.8x. So at x equals to 2 meters, so M equals 1.8 times 2 equals 3.6 kilonewtons meter. So from 0 all the way up in a straight line, reaching 3.6 kilonewton meters at x equals 2 meters. For the second segment to just before 5 meters, we are coming inside the distributed load. Now sum of moments about A, counterclockwise positive, equals 0. This internal M, counterclockwise positive, the internal V, at x from A, clockwise. So minus V of x times x. Now for the distributed load, again, because the distance at this edge is x from A, this segment length here is x minus 2. And we can replace this with a single load positioned at the midspan. Say F equals 0.8 times x minus 2. Now to calculate its contribution to moment, we have to know the length from A up to this midspan. This half section here is x minus 2 over 2. And thus from A, the length is L equals 2 plus x minus 2 over 2 equals x plus 2 over 2. So its contribution of moment at A is this F times the lever arm L clockwise. So minus 0.8 times x minus 2 times x plus 2 over 2 equals 0. Thus we have m of x equals v of x times x plus 0.4 times x squared minus 4. We denote v of x here because at this segment we can see that v is not constant but changes with x. Now we got this equation for the moment, and let's draw the curve. For m equals 2 meter, for v, we should see the shear at 2 meters here, which is 1.8 kilonewtons. So 1.8 times 2 plus 0.4 times 4 minus 4, which is 0. Thus we have 3.6 kilonewtons meter. And for x equals 5 meters, v is minus 0.6 times 5 plus 0.4 times 25 minus 4, and this equals 5.4 kilonewtons meter. Notice here that we have a quadratic equation, so the curve cannot be a straight line between these two values, but will be a parabolic curve. So between these 2 and 5 meters, where is the position of the maximum value? As we have discussed before, this must be when the shear is 0, which is at this x equals 4.25 meters. So for x equals 4.25 meters, v is 0. So we have only 0.4 times 4.25 squared minus 4, which is equal to 5.625 kilonewtons meter. So this is the position of the maximum moment, and the curve will pass through the peak and going down to 5.4 kilonewtons meter. For the third segment, between 5 and 7 meters, again we have passed beyond the distributed load, and so we can replace it with a single equivalent load of 2.4 kilonewtons. It sits at its fixed lever arm of 3.5 meters from A. Sum of moments about A, counterclockwise positive, equals 0. This internal m minus v times x minus 2.4 times 3.5 equals 0. With v equals to minus 0.6 here, m of x equals minus 0.6x plus 8.4. At x equals 5, that's minus 3 plus 8.4, which is 5.4 kilonewton meters. We start at the same point here, and at x equals 7, that's minus 4.2 plus 8.4, which is 4.2 kilonewton meters. So the graph is going down from 5.4 to 4.2 kilonewton meters. In the last segment, the free body now picks up the 1.5 kilonewton point load at its fixed lever arm of 7 meters from A. Sum of moments about A, counterclockwise positive, equals 0. This internal m minus v times x minus 2.4 times 3.5 is minus 1.5 times 7 equals 0. With v equal to minus 2.1 here, m of x equals minus 2.1x plus 18.9 at x equals 7. That's minus 14.7 plus 18.9 equals 4.2. At x equals 9, that's minus 18.9 plus 18.9, which is exactly 0. Exactly what a moment diagram has to do at a simple support with nothing beyond it. Alright guys, these are our shear force diagram and bending moment diagram for the problem. Now it's your turn. Pause the video here and try reproducing this whole beam yourself from scratch. Support reactions, shear diagram, moment diagram, and find the position and magnitude of the maximum moment. Then come back and check your numbers against what's on the screen. Don't forget to subscribe, like and share, and I'll see you again in the next worked problem.